Thank you very much for accepting our talk at ODSC. I want also to start by mentioning that Rajiv, who's been working with me a lot on this technology as well as NoGAN, is going to share some notebooks in the second part of this presentation. As the material I'm going to talk about here is now available as open source libraries on PyPy, and that's going to be what Rajiv will share in the second part of this presentation. So essentially the history or the background, I've been working quite a bit on GAN technology, so generative adversarial networks. Especially in the context of tabular data synthetization. So here I'm just going to be talking about, generation of tabular data, synthetic data actually. I've been working also on time series, geospatial data, some of the kind of synthetization, a little bit of computer visions. I'm going to be more involved also in NLM, but for here in this case, it's going to be what I call NoGAN, and it's called NoGAN because there is no GAN involved. There's no neural network actually involved. The reason I created it is after trying to fine-tune on various data sets, different GAN, Worcester GAN, conditional GAN, and stuff like that, so experienced a number of issues. I managed to improve GAN quite a bit, but to make sure that it runs with minimum amount of changes from moving from one data set to another. But anyway, that's why I started to do this NoGAN. There's actually NoGAN 2 and NoGAN 3. I'm going to focus here on one, the most tested of all, and with the main point, I guess, is how fast it runs compared to neural network based system that spend a lot of time on training. So because it's very fast, it also allows to lots of cost of saving. You spend much less time in the cloud, computations in the cloud. The tuning is also tuning the hyperparameters is also a little bit easier. Now I'll go through that. And then also very important contribution in this presentation is the discussion of the evaluation metric, which I believe everybody know about that metric. I call it the Kolmogorov-Smirnov distance. There's different variants of it. Some based on the probability distribution function. Here it's based on the empirical distribution function. It applies not just to NoGAN, it's actually quite generic. You can apply it to GAN as well. To compare, you use it to compare to the synthesization with the original data, the real data that is supposed to mimic. So the originality or the novelty, I mean, it's not really a novelty. It's a novelty in the sense that it's probably never been implemented before, is that it works here in any dimension, whether you are dealing with a mix of categorical, numerical features. So that's, I guess, probably the only time I've seen it implemented, truly implemented in multiple dimensions. What I've seen is that a lot of people use the same metric separately for each feature, and then they do a blend of the measurements computed separately on each feature. And I'll show you what kind of problems can arise from that. Essentially, you are going to rate some synthesization as good when they're not good because you miss the dependency, the full dependency structure between the feature. Anyway, let's move forward with my presentation after this brief introduction. I won't spend much time on on what is the synthetic data. I assume that many people here are familiar with the concept. Like I say, it's going to be focused on tabular data in this case. So people potentially interested are companies working with insurance data, healthcare data, cybersecurity data. These are case studies that we've been working on. Telecom is also an example in the education data set, a very interesting data set actually, and that's the one that in the notebook when Rajiv made the presentation, that's the one that's going to be used as an illustration in the notebook. So there are many different reasons you want to use synthetic data, and you use it to replicate the distribution that you observe in some real data. So create, some call it fake data. I don't like that word. But anyway, the potential goal are to benchmark algorithm. Myself, I use synthetic data a lot to create new observations that are potentially different from what you observe in the real data to check the limitation of some algorithms. You can use it to enrich your data set in the context of augmented data. So you have a bigger data set, which is not necessarily going to provide more accurate predictions. Actually, the predictions could be not as good, but you expect that the predictions, by adding the synthetic data to your training set to create augmented data, are going to be more robust because they've been trained on a more diversified kind of data. It's been used also for imputing missing values. Obviously, something that's very popular about synthetic data is addressing security and privacy issues. Like if you have credit card numbers, the address of some people, social security numbers and stuff like that. A good synthesization should take care of that. There's also another use when the data set is very expensive to acquire, in particular small data set. Like if you think about clinical trials, then you can augment your training set, but using synthetic data. It's also used to balance some data set, like in particular cases like fraud detection. Maybe 1 out of 10,000 or 4 out of 10,000 observations are fraud. That was about the ratio when I was working at Visa that we had. So if you try to detect fraud, you have a very small sample, a very small proportion of your data set that's fraud. And one way to augment it is to use synthetic data in creating synthetic fraudulent transaction. So what are the different techniques being used for data synthesization? I'm going to briefly explain a few of them. So the copula method, essentially a statistical methods, no neural network. Some do it with neural network, but you don't have to. What it does, it reproduces the correct marginal distributions that you observed in your real data, and it also correctly reproduces the correlations between any two features. It's rather simple and rather basic method, and it won't be able to reproduce complex dependencies patterns besides the linear pattern of the correlation, the cross correlations among the feature. Agent-based modeling is a little different. I think people, machine learning people, they don't really, they might not be that familiar with that kind of things because it's considered like operation research as opposed to machine learning. But essentially, it's to simulate complex systems like weather patterns or epidemiology. It's been used in this type of context. Parametric methods is another one that's heavy that can be heavy from a statistical point of view. For instance, Gaussian mixture models using the EM algorithm to find the components of the different components of your mixture in your real data, and then simulate from that particular Gaussian mixture. Right? Some are using neural networks to do that. And yeah, deep neural networks like GAN, Wasserstein GAN, conditional GAN, that's probably what people have heard the most for data synthesization. It's been doing a great job in contexts like computer vision, for instance. It's more difficult to use it in the context of tabular data, which is the reason why I came up with this no-GAN technology. And I'll briefly explain some of the problems that I had. Introducing white noise in the data might be the easiest one, but you need to do it right. For time series or geospatial data, I've been using some interpolation methods actually, but I'm not going to go into the details. Why no-GAN and where does it fit? So I already mentioned why I created it. It's a little bit like kind of what NoSQL is to SQL. It's running much faster. The better results are based on very challenging the evaluation metric that I was talking about. So actually, depending on the choice of the hyperparameters and depending on how you do the no-GAN, you can have a full exact replication of your real data set, which is not what you want to do, of course, but that tells you how far it can go in terms of mimicking the distribution in the in the real data. And I will explain how to not go in that direction, because that's not what you want to do anyway. It's also, in my opinion, the hyperparameters are easy to understand, easy to fine-tune, even in a version of no-GAN that I'm going to talk a little bit about, which is a Gaussian no-GAN. That's more hyperparameters being introduced there, but they're still easy to understand and fine-tune. And the future actually is to have auto-tuning, where the user does not need to worry about, only the expert user could play with the hyperparameters, but for most users, it's going to be auto-tuned. So I mentioned the case studies: telecom, insurance, healthcare, cybersecurity, education. In addition to that, I've also tested it on made-up data set that are very challenging, very hard data set to compare different vendors, for instance, how they do on that type of data set, and see compare different methods, including no-GAN. And like I said, there's now some open source available. I think when I wrote this particular slide, that was a while back. So there's a library for the evaluation metric, and now there's also a library for the synthesizing the data. Here it illustrates the evaluation metric. So that was actually the challenging data set I was talking about. It's 8 dimension, but here you only see 2 dimensions with the scatter plot. And in these 2 dimensions, you see 2 concentric circles. So that's where the real data is located. If you look at the top corner on the left, then you have 5 synthesization from different vendors, are also included SDV, and all these synthesizations, if you use most evaluation metric, they're going to be rated as excellent. Even for, obviously, for instance, SDV seems to be doing, it does do a very poor job. When I'm talking about SDV, so it's Synthetic Data Vault Library, and to its defense, I have to say that I used the default parameters. I didn't spend considerable amount of time in SDV. SDV might be able to do a better job if you use more advanced parameters or tuning. And here in this case, I remember that it used a light version of gradient boosting. I don't know if that's explained the very poor performance here, but my point is that many evaluation metrics are going to rate everything here as excellent because what you have, and even the copular sensitizers that I used would result in something in between the best and the worst of what you see there. But the marginal distributions are perfectly replicated. There's absolutely no correlation at all in at least in these two dimensions. The correlation between the two features is 0. Everywhere in this 5 synthesization, correlation is 0. Marginal distributions are correctly replicated. So if you use some basic, if you use these evaluation matrix, it's going to look like you did a great job, when in reality you didn't do a great job. And this is actually what NOGAN did on the Circle dataset. Now I've tried to summarize the algorithm, how NOGAN works, in just one slide. I'll try to be my best to be brief here. It's not that complicated in some way, but essentially you're going to browse your data set only once. So that explains the speed. You first need to create a bin structure in the feature space, and in high dimension, the bin structure, so multivariate bins, static bins covering a portion of the feature space where your points are located. In high dimension, that portion of the space is extremely tiny compared to the whole space. So it's the curse of dimensionality. And this NOGAN algorithm exploits that, in the sense that doesn't care what's really outside this the working environment, the windows where all the points in high dimensions are located. So when you create multivariate bins, which is some analogy with decision trees or XGBoost, you are not going to create more bins than there are observations in your real data. Now, there are two problems. So you have, let's say you have 10,000 bins. That's the structure you come up with. Eventually, you have 10,000 multivariate bins. You can put everything that's categorical into just one new feature. That's the subject of the next slide. But so you have a rather small number of bins. You know the center of each bin is determined by the real data, and how many points you're going to generate in each bin is also based on the proportions that you observe in the real data. So obviously what you do in this case, you're going to choose a multinomial distribution that is as many parameters as there are multivariate bins. The parameters here are the proportion of points, the proportion of observations for each of the bins. So you use that multivariate, the multinomial distribution to generate the point counts in each bin, and then when you have say 5 points in a particular bin and you need to generate them in that particular multivariate bin, the initial method was to a uniform distribution in that bin. Then we worked on different strategies. Gaussian, NOGAN actually uses a Gaussian distribution. With a Gaussian distribution, it actually provides better results for numerical features. What you get is that some of the points you generate in the bin where these points are supposed to be, some of them may be generated in neighboring bits. So it creates a richer data set by using something older than a uniform distribution or bounded distribution, forcing all these points to stay within the bins where they're supposed to be. Why is GAN so fast? So I think I pretty clearly explain and convey the messages why it's so fast. So let me move to the next slide, which is what do you do when you have a bunch of categorical features, which is typical. I mean, so in the case studies that I've been using, most of the features actually they are categorical. They did different ways to do that. But one thing that they've been working quite well, it still requires some refinement, is to use, I mean, this is not something new, it's something well known, so I won't spend much time on this. I call this smart encoding, and I just give you an example here where you have two features, gender and region. You create codes for each combination of categorical values, like male northeast 0, male southwest 1, and you create those codes incrementally as you browse your real data set. So you're going to end up with no more codes than there are observations. Some codes might have very, very few observations, and the idea is to bundle them together. It's not been done yet, so something for the future. But so the thing about this is, if you have categorical features, if you have 40 features and each feature can take on 5 different values, I mean, the potential number of categories that you can have is trillions of quadrillions. I mean, because of the dimensionality, the curse of dimensionality, this is a combinatorial problem. But by doing this, you avoid that, and you end up with something entirely manageable and fast. So one important part in all the tests that I've been doing is I've been using cross validation, and this is particularly important in the context of no-GAN, because if you want to with no-GAN, you can perfectly replicate the exact real data set, which is not what you want to do. So in order to make sure you're not overfitting and you're creating problems by getting too close to the real data set, you just split the real data set into 2 parts. The training set, you use that to train. I don't like to use the word train. It's not really, by train I mean building the multivariate bin structure. So you use the training set. 50% of your real data set is the training set, and you use that to synthesize your data. But then the synthetic data that you have obtained, you compare it, you evaluate the quality, not by comparing to the training set, but to the other 50% that were not used in the training set, which is called the validation set. So you avoid overfitting to some extent with that. What I've seen in practice is that the 50% corresponding to the training set and the 50% corresponding to the validation set, they are 2 different data sets, of course, but they're kind of similar. So that might not be necessarily the best way to do it. I think what a lot of people are doing, let's say you have a clustering algorithm, you have a response in one of your features, the response. You use some predictive algorithm. What you want to do is add synthetic data and see how the predictive algorithm is going to perform without the synthetic data, on the synthetic data alone, and when blending both. So that's an approach that's been used by a lot of people in various contexts, not just GAN, but not just no-GAN, but GAN and so forth. So I've actually spent a little bit of time on the best evaluation metric. So I don't think if I have anything else to add to it. So essentially, in one dimension, that would be the typical Kolmogorov-Smirnov distance. There's two features that come with the evaluation metric. It's designed in such a way that the value is between 0 and 1, with 0 mean the distance between synthetic data and validation data is the distance is 0, mean it's a very good replication, and 1 being the worst. Then there is also something else that goes into that metric. It's adjusted for dimension, because if you use, let's think of if all your feature were totally independent, you would expect that the empirical, the distribution would take a value around 0.5, that'd be kind of a standard type of value you would observe for one feature. Now you have 20 feature, a typical value would be 0.5 at power 20. So that's very close to 0. So you're going to get results always very close to 0 if you don't do anything to adjust for dimension. So it contains something about to avoid that problem. And this is, I just wanted to show some results about NoGAN. That's the telecom data set. And a few are scatter plot comparing the real data with the validation data with the synthetic data for. And then you have the histograms that show a same thing, comparing synthetic with validations with a very good replication of the distribution, the univariate distribution. And so that's the KS, Kolmogorov-Smirnov distance, the multivariate distance. It's just a single number that summarizes very well everything. So you just need one single number. But you can also do a plot of all the values of the two ECDF, the empirical cumulative distribution functions, the one attached to the validation set and the one attached to the training set. So, and then you get this type of, I don't even remember, I should know in statistics, are they called QQ plots? I don't remember, I should know because I have a PhD in statistics, but anyway, that's kind of a standard scatter plot. I don't have much time left, so I'm just going to be quickly mentioning the main hyperparameter. It's a vector that is as many components as there are features, and for a particular feature, the value that you're going to choose in the hyperparameter is how do you want to slice that feature in a number of bins. And here I'm not talking about multivariate bins, I'm talking about univariate bins because before getting to the multivariate bins, you start with univariate bins. So if you have a large number of univariate bins for a particular feature, eventually you're going to get better results, better evaluation metric, but risk of overfitting and stuff like that I already mentioned. But an important question that I've been asked multiple times is, let's say you have a category, a feature is a category, there is 5 different values, one of them is just 1%, maybe fraud, it's just 1% of your data set. And you do the synthesization and then you complain, it didn't produce any fraudulent, it didn't produce anything in that category. So the way, and this is where I'm talking about explainable AI and some intuitive stuff. If you want to cover values that are rare, let's say 1% of your observation, in this case, you need for that feature to get a value in the upper parameter, that's going to be essentially 1 divided by 1%. So which is pretty straightforward. Gives you a rule of thumb on what to do to make sure you're not going to miss a small portion of the data set. In some cases, it's unimportant. In some of the cases, like fraud detection, it's important. And quickly discuss the Gaussian no-GAN just by an illustration. You can see on the left side, that's the validation set, and middle and right side, that's the synthesized data. In the middle, it's the initial standard no-GAN. In the right, that's the Gaussian no-GAN. If you look closely at the middle scatter plot at the top, you're going to see that this kind of a boundary, the bottom boundary, is a little bit bumpy. Like you can see, some kind of small segments, not very visible, because I chose hyperparameters that are large enough to kind of avoid that problem. If you would pick up hyperparameters that are much lower, it's going to be very visible, and you're going to realize, yeah, it's obvious that there is some kind of multivariate bins, which in the feature space are hyper rectangles. It would be rectangles into dimension. It's going to become obvious. The Gaussian no-GAN eliminate much of that problem without having to boost the hyperparameter values to high. Yeah, I don't have the time to go into detail of this. No-GAN announcement. I'll just make one comment about how to enhance no-GAN GAN, or anything actually, so not just no-GAN. So one of the problems that I found is that many of these systems, they use in one way or another a percentile or quantile functions, typically implemented in Python, the default quantile function available in Python. And so the minimum for the quantile is the minimum in your data set, the real data set, and the maximum is the maximum in your real data set for the feature in question. That means you're unable to generate data outside the range of observations. I mean, the Gaussian no-GAN fixes to some extent that problem, but that's something we're going to work in the future, and that applies to GAN as well, is to use quantile extrapolation that are not limited to the minimum and the maximum. That should fix the issue. Quantile extrapolation is not something I invented myself. It's been quite known for some time in the statistical community. So I have to do some search about that to make sure I'm not reinventing the wheel for that. And last slide. So I would like to thank a lot of people who've been working with me on case studies, bringing a data set, asking a lot of challenging questions. And actually, Rajiv is here today, and he developed the 2 open source libraries. He's also working right now on a web API where you can upload your training set and get synthesized data. And it is just going to be talking about this very shortly. And I think that's it for my presentation. So we can now switch to Rajiv unless there are some questions, but I'm done with this part of the presentation. The slides, if you want to get the slides, I'm fine sharing. This is public, so you can ask to the organizers to get them, or from myself. I have no problem about that. So yeah, the 2 main questions I see here is about what are the potential drawbacks of using synthetic data. I see some drawbacks might be that you will not use synthesizing something that's too close to your real data. So you're expecting, for instance, you use synthetic data to avoid algorithm bias, to not penalize minorities and stuff like that. But if your synthetic data replicate very, very well what's in your real data, well, it's going to be replicating the bias as well. So that is something you need to be careful about. Some of the issues is that despite the fact that you try to hide and transform all the fields that are related to personal information, you still need to be careful. So that may not be that obvious to do. Like if there is a strong outlier in your data, people might kind of reverse engineer, figure out who that guy is. I was talking in this case the insurance data set. There was a guy or a woman, I don't know, who a massive amount of health expenditure. You want to make sure that somehow, if you have data with strong outliers like that, it's impossible to recover in one way or another who that person might be. So that's another issue with synthetic data. What else? I mean, I've seen for tabular data, yeah, we're talking with tabular data, and the reason why I created NoGAN was that it takes time to train neural networks. I mean, you can do it in GPU when it costs money. And the results that you get can be quite different from one sensitization to another. By the way, something I mentioned forgot to mention is all the sensitization I've been doing here, including those based on GAN, they all replicable. So there is that. So what else? So these are the first four that come to my mind about synthetic data. Yeah, another one is you might think that you have great synthetic data, but actually you don't. And that's the example I mentioned with the circle, because you're using evaluation metrics that are poor, to put it this way. I don't know if I've answered all the question.
I'll be giving a very quick demo. I think we don't have much time left. I'll try to make it as quick as possible. I'll just try to mention the packages we are using, and I'll take a sample data and just show how we can train the data on that and create synthetic data, and then evaluate on the validation. And at the same time, compare with an existing GAN library and see how the data is synthetic data is produced there and how good that is. So there are two major packages which we are using, and this you can, if you want more details, you can look them up on PyPy, and there is a link on GitHub link as well if you want to go through the code. So as usual, we just in the usual way we install the packages and then import some of the required packages and objects. Set some seed, the values you'll be using during training and generation. I'm using an existing data from UCI, the Student Academic Success, and I am extracting about 21 features here for our synthetic data generation. If you look at the columns here, right, most of them are numeric. There's only one categorical column, that is the target. But in NoGAN, we can always there might be. I mean, in the tabular data, we may have a lot of numerical data which we may need to consider them as categorical. So we can do that here. So in this case, if I take an example, about 11 columns, I consider them as categorical. In some of them are numeric as well, right? And as Vincent had mentioned before, we do a 50-50 split here, training, and then we validate the training on the training data and evaluate the training and the validation synthetic data, and the same we do with the generated data. Before doing that, our model works completely on numeric. So what we need to do is we need to encode the categorical columns And if you see here, I consider about 11 categorical columns which are encoded using the wrap category columns function. And once we do that, we pass the data set and the categorical columns list. We get a wrapped data, which is if you see here, we have about all these are the numerical ones, the top ones, and there's one encoded categorical column, which is the one which has encoded everything into one single categorical column. And I'll just show you briefly. Okay, after this, once we call this function, it returns one dictionary as well. Now, this dictionary is used to expand once we generate the synthetic data, we need to expand the categorical columns back. So this will be used for that. So I'll briefly show you how they look. So Vincent had mentioned in the slide, right? We encode the categorical columns into key value pairs. So if you see here, this is the key and these are the values. And we use this information to expand the categorical columns once we generate the synthetic data. And one of the hyperparameters is the bin values. Right now we started with 100, and this can be changed. This needs to be tuned. This is a tunable parameter. So right now in this example, I have kept 100, which is a hard-coded value, and I instantiate the model, send the trained data, the wrapped data, which has the encoded categorical column, and fit the bins here. So once this is done, we can start generating the synthetic data. Now during generation, we have different values. I think Vincent could not cover something. There's something called a stretch value. There are stretch values and stretch types. So I won't go deep into that, but these are all hyperparameters which we can use to generate the synthetic data. So once we generate the data, we can just we need to evaluate that, right? And that is done using the multivariate ECDF. This multivariate ECDF, this function, it generates the different nodes using query strings. I'll show you exactly what happens here. When we pass the wrapped validation data as well as the synthetic data, and we mention how many queries we need to create. These are the frequencies. And once that is generated, you can see here, these are the queries, some of the queries. This is what is used for multivariate ECDF calculation. I think for more details, you can always contact me or Vincent. We can give you detailed demo on this. But in the interest of time, I'll just make it fast. So once this is generated, we check check how the base versus the training versus validation and the synthetic versus validation, how they fare. And if you look, most of them are near, a couple of them are near the base statistics, and this is what we aim for. And when we see that, we can always increase the nodes, and this will give more better accuracy. Once we do that, we can get back the data, the categorical columns, encoded categorical columns back using the unwrap category columns function, using the IDX2 key train dictionary, which we had calculated earlier. So if you just once we generate that, we can take a look at the distribution. So this is the synthetic data which is generated for admission, grade versus age and enrollment. The correlation is almost similar. And this one is the synthetic data, and this one is the validation data. If you look at this, correlation is similar, even with the other numerical columns as well. Similarly, the proportion of the target column, which is a categorical column, you can see the synthetic versus validation is almost similar. Now, I tried and fitted a CT-GAN on the same data set. And if you look at the scatter plot, you can see that the correlation is not that great as we saw for the no-GAN. And similarly, even the proportion of the target columns, they are not very similar. So this shows that no-GAN works pretty fast. I mean, pretty well as very fast. If you see CT-GAN, it takes about 2 minutes or so for this 200 epochs, while the no-GAN took about 1.2 seconds to complete. And I think that's it. If you have any questions, please. Vincent, do we have any other questions?
No, it's a great presentation. Thank you so much, Rajiv. I forgot actually my presentation to mention the base KS distance. I don't know if I have much time to go into the detail, but essentially, so when you do your sensitization, you have a validation set and you have the training set. So you have 3 data sets. You compare the results between the sensitization and the validation set. But if the validation set is very different from the training set, your splitting didn't go well, or some issue happened. So in the end, what's important is going to be the base Kolmogorov-Smirnov distance. So the evaluation metric that compares your validation set with your training set. And you want, so that's your base metric, tells you how different those 2 data sets are. And you want your sensitization to have an evaluation metric that's about the same as the distance between the sensitization, between the training and the validation set. So to put it this way, if you have a training set that's very different from the validation set, you should not expect the sensitization to be a good match for the validation set. The other thing also that I didn't mention, so Rajiv mentioned 1,000 nodes. So the way that the evaluation metric is computed is by approximation, so it's an asymptotic result. What you want to do is we need to kind of further optimize the speed of this procedure. Actually, the no-GAN is very fast, but the evaluation metric is the slow portion of it. Still, it runs fast, but I guess we can do faster. Especially, I would encourage to use 10,000 nodes as opposed to 1,000 or even 100,000. What you want to do is test 1,000 nodes, 10,000 nodes. Is there a big difference? There should be a small difference, not much. And then by the time you reach 100,000 nodes, pretty much there's no more differences. It's going to be particularly important when when you make comparison and you get very good. When you get very good results, you might want to increase the number of nodes. In some instances, actually, the distance between a synthetic and validation was lower than between synthetic and training. That can happen, but should be unexpected, should be rare, and it should not be much lower. It should be about the same. But I've noticed in many times that actually increasing from 1,000 nodes to 1,000 nodes eliminate, which is kind of a little bit of oddity of the situation. Everyone for attending this this talk, and hope you enjoy it. Thank you very much.
Thank you. Bye.